Nice, but so welcome. We're going to be talking about considering multivariable thinking in introductory and intermediate statistics courses today. And we do acknowledge and thank the National Science Foundation for supporting this workshop. Let me remind you of the workshop goal or tell you of the workshop goal. If I can figure out where my mouse is. For Pete's sake. Sorry, I lost my mouse and I'm still not finding my mouse. So the workshop goal is to provide faculty participants with ideas and activities for helping their students to develop skills of multivariable thinking. If you were with us yesterday, thanks for coming back. You know our three presenters yesterday were Nathan, Todd, and Laura. If you weren't here yesterday, you're very welcome today, of course. And you can find the recording from yesterday on the EA Post website. And I'll put a link to that site in the chat unless somebody beats me to it. Today, as I mentioned, our three presenters are all in the Department of Statistics at Cal Poly in San Luis Obispo. First will be Karen McGoy, followed by Soma Roy, followed by Beth Chance. Today is focusing on bridging between introductory and intermediate courses. But a lot of what you see today is going to be very appropriate for a typical introductory Stat 101 course. Some of what you see today will be more appropriate for a second course, a follow-up course. We'll have 3 sessions today. I think today the presenters are not aiming for 45 minutes each, but we will take 10-minute breaks between the sessions, and we will have time for Q&A at the end. But you should certainly feel free to type questions in the chat and comments in the chat as we go. And the recording will be posted either later today or tomorrow, and I'll send out an email message about that once the recording is posted. So without further ado, let me ask Karen to take it away.
Hi, everybody. Welcome to day 2. My name is Karen McGoy, and I, as Alan said, am in the Department of Statistics at Cal Poly in San Luis Obispo. I am going to talk about um, assessing variation due to random assignment. So I think Laura talked a little bit about designing experiments yesterday. I'm going to talk about that a little bit more. The first example, we'll look at a comparison of 2 groups on a quantitative response. And the second example will be a 3-group comparison, so sort of moving into analysis of variance. And then towards the end of this session, I'll get into a block design. So just a little bit of recap on multivariable thinking. The ideas that we want students to be able to sort of do in this arena would be to think about what variables are being studied and measured, what variables will likely contribute to variation in the response, and how do we deal with those variables in a study, right? Things like inclusion criteria, but then the sorts of limitations that those place on the scope of inference. In a designed experiment, the variables that can be controlled or randomized or blocked, and the idea that to isolate the relationship between 2 variables requires accounting for many other variables as much as possible, and there's lots of different ways to do that. So the first study that I want to talk about comes from the New England Journal of Medicine. It's a study which investigates the effects of Tai Chi on postural stability in people with Parkinson's. Parkinson's disease has 5 stages. Stage 1 is the most mild, and stage 5 is the most severe. In this study, the actual study used 3 treatment groups. But I'm going to start this first example using only 2 of the treatment groups, which are Tai Chi and a stretching treatment. So we'll start with 130 people with Parkinson's in stages 1 through 4, ages 40 to 85, with medical clearance to participate in the study. So the researchers randomly assigned 65 participants to each of the exercise programs for a period of 12 weeks. And then they controlled the weekly frequency and duration of exercise for all of the participants. And then both before and at the end of the study, the functional reach was measured in centimeters for each participant. Functional reach is the distance that a person can reach out away from the body to retrieve an item without losing balance and falling over. And so the response variable here is going to be the change in functional reach. So just some background questions for students as we get into the example. So being able to answer things like the response variable, the explanatory variable, the type of study and type of conclusions. So here, change in functional reach is the response. Exercise program or exercise type is the explanatory variable. It's binary with 2 levels. This is an experiment. And then some discussion of the type of conclusion that we could potentially draw. If we find a significant association between the response and explanatory variable, we might tend towards a cause and effect conclusion. Based on the fact that this is a well-designed controlled experiment with replication using random assignment of treatments to participants. The study also randomized other things such as the order of testing. And then sort of maybe previous to this example, we've probably discussed with students the idea that random assignment, or at least the goal of random assignment, is to keep extraneous sources of variation from becoming associated with the explanatory variable. And so the idea then is that random assignment sort of limits the potential for confounding variables or alternative explanations for the association that we might uncover between the response and explanatory variable. And so I would typically show my students a table of the demographic characteristics. This was provided in the journal article, sort of showing here, because the actual study was 3 groups, things like age and sex and body mass, Parkinson's stage, all of these sort of extraneous sources of variability, which may impact the response here. And the researchers found there was not really any significant differences among the treatment groups for these responses. So sort of indicating that maybe random assignment has done a reasonable job here with these particular variables. So sort of getting into multivariable thinking, explaining variation in the response, I would show my students just a histogram of the change in functional reach values from the study. And then I would ask my students, what are some possible sources of variation in the change in functional reach? So I'll pose that question to you. Here is the actual data for these 130 participants, and what do you think is causing some of the variation that we're seeing in those outcomes? So if you have any ideas, just put those in the chat. A few people typing in, thank you. And so I feel like this is a pretty accessible example for students. and they do a reasonable job of coming up with quite a few things, as you are, variables that may be contributing to that variation. Uh, so then let me stop now and pose another question for you. What would this histogram of the change in functional reach look like if there was no variation in those change in functional reach values? And so what would that histogram look like if there was no variability in the change in functional reach? Yeah, so hopefully we can sort of get at the idea that it might look something like this, right? So all of the change in functional reach values would be the same for every participant in the study, and so those might stack up at a particular value. In this case, I just stack them at the mean of 2.88. Okay. So I think, that's important to sort of contrast those two ideas for students, as we're talking about what can cause variation in the response. And then the idea at this point would be to sort of organize all of these sources of variation, again, into a sources of variation diagram. So we're talking about the response, which is change in functional reach. We've got some inclusion criteria, and we have some variables that the researchers held constant within the design of the study for everybody in the study. Our source of explained variation here is the exercise program. And then I would take all of those things that you all brainstormed for me and sort of put them into this sources of unexplained variation column. And I always like to include unknown here as a potential source of variation. And then at this point, I would like my students to sort of start thinking about the idea of a model. And maybe the simplest thing to do is to sort of use a word model and get across the idea that we're going to try to model those change in functional reach values using exercise program. But we're doing this in the presence of lots of unexplained variation. And so that unexplained variation is gonna play a role in, of course, the statistical inference. So here's the fitted model then. So just breaking out these change in functional reach values according to the two groups here. And then, right, we might ask the question, does the type of exercise explain any variation in the change in functional reach? And so based on the fact that those means differ, right, we might come to the conclusion that there is some amount of explained variation, right? There are differences in how people are responding based on the treatment that they received. But then there's also some leftover or unexplained variation that we see after accounting for these two treatment groups. And so we're sort of taking that sources of variation diagram, which had a source of explained and a bunch of unexplained sources, right? And sort of showing students how that partitions here with the pie chart. And then, we can sort of easily transition into statistical inference if that's our goal. I would want students at this point in my class to sort of understand that this theory-based test or the the two sample t-test is really just a standardized ratio of explained to unexplained variation. And so we see that explained variation represented by that difference in the two group means. And then we see that unexplained or leftover variation accounted for by those standard deviations within the two treatment groups. And so we see that whether we're thinking about the unpooled or the pooled version of the T statistic. Right now, if you're interested and would like to think about simulation-based inference in this sort of context, then we might ask the question, what statistic could we use to measure how different the two group means are, right? And so we've sort of already addressed that with that difference in means for the two treatment groups, which is 4.03 centimeters. If we're going to assess the statistical significance of that outcome, then we could ask students the question, for these data, what kinds of differences in means could we expect just from the random assignment process alone, right? And so I might sort of break that down for my students and say, okay, well, what was the goal of random assignment, right? With all of those extraneous sources of variability, what are we hoping random assignment does for us, right? And the idea here is that if we were to shuffle the observed change in functional reach values and then re-randomize them into the Tai Chi and stretching groups, then we might expect to see something that looks more like this, right? Where the mean in the stretching group and the mean in the Tai Chi group are much closer together, right? And so we can sort of repeat that shuffling and re-random assignment process many times to develop a distribution against which we can assess the statistical significance of that observed difference in means. So I'm going to go to the multiple means applet. Maybe somebody could put the link to this in the chat if others want to go there. Let me find it here. So when you load that applet, it'll look something like this. And I'm going to clear this data. And we have preloaded the Tai Chi data in the background here. So if in the enter data window, if you type Tai Chi with a capital T and a capital C, 2.txt, then that will give you access to this data. And you'll need to select use data. That will bring the data into the enter data window. And then if you select use data again, then that will actually load the data into the applet. And so now we see the dot plots. You can add box plots if you like. There's some summary statistics down here. And then what comes up by default is the observed difference in means 4.037. So there's lots of other statistics that you can talk about with students if you like. But I'll focus on just the observed difference in means. And so in the right-hand panel of the applet, if you select show shuffle options, and then I'm going to actually turn on the plots. And then if I'm teaching simulation-based inference with my students, I would have them do some sort of tactile shuffling, where maybe we have little index cards and we've written the response outcome on those cards, and then they shuffle the cards and deal them into two groups. That's a little bit hard with 130 observations. So we might do this with a smaller example initially. But the nice thing about this applet is that if you select shuffle responses, the students can actually see that shuffling of the outcomes and kind of the re-random assignment into the two groups. They get a summary of that one shuffling, and then the difference in means here is computed and plotted over here in the right-hand plot. And so we can let students do that a couple of times, right, to sort of get the idea of what's happening, and then maybe crank that up uh, to a large number of shuffles to sort of create that distribution of what could happen just by random assignment alone, right? So the variability that we're looking at in this distribution is coming from the re-random assignment process. And then we can enter that observed difference in means, and the applet will count the number of shuffled outcomes that were as or more extreme than that observed difference. If we'd like to do a two-sided test, then select beyond, and there were 0 out of 1,000 here that were as or more extreme than 4.03. So I would, at this point, tell my students, I don't want you to report the p-value as 0. We only did 1,000 shuffles here, so maybe say that the p-value is smaller than something like 1 in 1,000, which certainly is enough to make a decision here. So I'm gonna bring you back to my presentation here. So that's kind of, even what you could do in a first course in statistics. If we're moving into the second course now, or maybe your first course, you also have an opportunity to compare more than two groups. But certainly in the second course, we would get into more than two groups. And so in the actual study here, the researchers used 3 different exercise programs: Tai Chi, stretching, and a resistance training. They had 195 people. 1/3 of those, or 65, were randomly assigned to each exercise program for a period of 12 weeks. So everything about the study was the same as what you've already learned, except now we have 3 groups. So that sources of variation diagram that we were talking about earlier is the same. For this example, we've just added a group here, resistance training. And so that model that we talked about earlier is also the same, right? We're still trying to look at this relationship between exercise program and change in functional reach in the presence of all of this unexplained variation. The fitted model now has 3 groups. So we have 3 means. And so again, we might ask the question, is exercise program explaining variation in the change in functional reach? And based on what students, have already learned, right? Hopefully they can say yes to this question, because those means differ among the 3 treatment groups. But there's still lots of leftover or unexplained variation as represented by the standard deviations within those 3 treatment groups. So I'll start with simulation-based inference this time. So we need to think about what statistic we could use to measure how different the 3 group means are. If you're familiar with analysis of variance, you know that ultimately we'd like to get to the F statistic, but that's a big leap for students at this point, and wouldn't expect the students to come up with the F statistic right off the bat. Does anybody have any ideas about what statistic, a single number that we could use to assess or capture how different those three means are? In chat, if you have an idea. Yeah, so I'm seeing R squared, standard deviation of the means, for sure. And in a second course in statistics, um, we have talked about R squared at this point in the course, and so R squared is a good one for students to use here. Standard deviation of the means also can work very well. Another possibility, right, might just be to take the mean of the pairwise group differences. And so, right, let's look at how different each mean is from each of the other means. Let's take the absolute value so that we don't have to worry about, some of these differences are positive and some of these differences are negative, and the trouble with canceling, if some are positive and some are negative, canceling each other out essentially, and dampening the size of the statistic. So maybe something like this could be used, right? So the observed mean of the pairwise group differences, I think, if I've done my math right, is about 2.691 here. And so we can talk about, the size of that statistic on its own, right? So if there were no differences in the group means, what kind of value would we get for this statistic? And so, students hopefully can get to the idea that, well, that would mean that all of these pairwise differences are zero, and so that statistic would be zero. And so then we can think about if we were to repeatedly shuffle the observed change in functional reach values and redistribute them, reassign them to the three groups, what sorts of differences, or excuse me, what sorts of means of the pairwise group differences would we expect? And so hopefully students, can get to the idea that that the differences, or that statistic should be small. So I'm going to go back to the multiple means applet here. And so if you clear out the data, I'll turn this off as well. Go into the enter data window and now type in taiji3.txt. So capital T, capital C, taiji3. And again, we're going to select use data. That brings the data into the enter data window, and then use data again. And now we've loaded the data into the applet itself. So I always ask students to check the means and make sure those coincide with what we're expecting here. And then we can think about this shuffling process. I'm going to change my number of shuffles to 1. The statistic that we're looking at here is the mean group difference. And so we shuffle the data, and now we see the shuffling of those observed change in functional reach values back into the three groups. So we're getting new means, which are much closer together here, and this shuffled mean group difference of 0.55, which is going to get plotted over here on the right. I'm going to delete the 4.03 because that doesn't make sense anymore. And then, right, let students see this a couple of times. And then again, right, we can increase the number of repetitions to some big number, right, and let them see that now we have this sort of skewed distribution, right, where we have lots of values here close to 0, and then this sort of tail off to the right. And we can use this to, right, assess the statistical significance of that observed group mean difference value. So I'm gonna go back here, right? If we want to get into a theory-based test, which in a second course we would, but in a first course you could just sort of stop with the mean of the pairwise group differences if you wanted to. It gives students a nice introduction to analysis variance, and this idea of dealing with more than two groups. But if you want to move into a theory-based test, we're going to think about the F statistic. It's nice to be able to sort of compare that to the T statistic, which they've already seen. The F statistic, again, is just a standardized ratio of the explained to unexplained variation. But to get to the F statistic, we actually now need the sums of squares. And so some time needs to be devoted to sort of developing, and thinking about what those sums of squares are, how they're computed, and then showing students that the ANOVA table is really just this partitioning into explained and unexplained variation that we saw previously in the sources variation diagram and the pie charts. And now we're just sort of tabulating this variation and computing variances, and then the F statistic, and then a theory-based p-value from an F distribution with 2 and 192 degrees of freedom. So the F statistic can also be derived from R squared. I haven't shown that to you here, but that's a nice transition for students to sort of move from, assessing the significance of R squared and then using R squared to compute the F statistic, and then assessing the statistical significance of the F statistic. Okay, so in the interest of time, I'm going to keep going, and then maybe if there's questions, we can have a few minutes at the end to get those answered. So the next example that I'd like to talk about is designing out a source of variability. The previous examples used random assignment of treatments to experimental units to sort of protect against the possibility of confounding variables. In this example, we're going to use blocking to design out an inherent source of variation in the experimental unit. So for this example, I'm going to talk about strawberries and the storage of strawberries after they're picked. The explanatory variable is storage method. There's 3 storage methods: an air storage, a modified air, which uses a percentage of carbon dioxide, and then a control condition. The experimental unit is a clamshell of strawberries. The storage time for air and modified air was 42 hours, and the control clamshells were measured immediately after they were packed. There were, in the actual study, I think there was something like 32 different varieties of strawberries that were used, but in this example, we're using only 5 different varieties of strawberries, and that's to keep the data set quite small, because we're going to ask students to do some computation. The idea here is that there are large differences in the inherent firmness of strawberries for these 5 different varieties. And the response variable here is what I'm going to call the clamshell firmness. It's measured in newtons. So the researchers took a probe and they probed each of the berries in the clamshell. So there's actually a measurement for each berry, but then they averaged those and came out with a response, a single value representing the firmness of the clamshell. which is really just the average firmness of all the berries in that clamshell. So that's a nice discussion to have with students in thinking about kind of, true replication versus pseudo replication or subsampling. All right. So then, again, getting students to think about the sources of variation diagram, um, the explained variation inclusion criteria, what was held constant by design, and then again, getting them to brainstorm, what are some sources of unexplained variation in the firmness of the clamshell. And then taking them to that sort of word model again, we're going to try to explain variation or make some predictions in clamshell firmness based on the storage method, which has 3 levels, but we're going to do that in the presence of unexplained variation. So here's the fitted model, at least in terms of the previous sources of variation diagram, right? So here, a higher mean firmness is better because it means that the strawberries are sort of lasting a little bit longer. And so just by inspection of the means, we see some differences. The modified air has a higher average. That's because the carbon dioxide actually has the impact of making the strawberries more firm than what they were even when they were first picked. So if we fit this model and we start thinking about statistical significance, the F statistic is 1, the p-value here is 0.3981. So we do have some explained variation. The R squared here is about 14.2%. But I would ask my students, why do you think we're not seeing a statistically significant outcome here? And not that that's necessarily a bad thing, right? But just getting students to think about why the outcome may not is not statistically significant, right? And so hopefully, right, because that F statistic is about 1, we're landing on this idea that, right, that standardized ratio of explained to unexplained variation, right, that unexplained variation is quite large. So, right, is there a way that the researchers could design their study to take a source of variation, for example, variety, into account, right? And so using that kind of phrasing into account pretty loosely here, not really having defined that before, although students have already seen a paired design, and so we've sort of talked about maybe taking person into account or some language like that. But, right, landing on the idea that it would be nice if we grouped the clamshells by variety and then measured each treatment on each variety in this sort of block design, right? So this is actually a randomized complete block design. There's one replication or one replicate of each treatment within each of the blocks here. So once we kind of get to this design, then the analysis needs to match the design. Okay, so that earlier analysis that we did, where we only had one explained source of variation, that analysis is not appropriate here because the design now has accounted for the blocking variable here or the variety. So the idea then, there's kind of 2 ways that we can think about analyzing this data. So the first is to quantify the variation explained by variety and then remove it from the error. right? So we're literally going to find out how much variation variety is responsible for, and we're going to move that out of the unexplained column into the explained column. And then what happens, right, when we do that is the sum of squares error is going to go down. So that amount of unexplained variation drops when we take out the variety to variety variation. And the reason we can do this, right, is because of the block design that's been actually run in this study. So we're going to then, right, think about predicting or explaining variation in clamshell firmness based on storage method and variety, right? But we're still going to have some unexplained variation that we have not accounted for. So at this point, I would have my students actually work through the computation of the sum of squares for variety. And so they would have sort of already had experience with computing sums of squares, for example, for the storage method. So this is new, but it's not 100% new because they've already done it with an explanatory variable, right? So the idea is that because we've got several outcomes, three in this case, on each variety, then we should be able to find an average response for each variety. And then once we have that average response, we should be able to find the effect of each variety. And so the effect, by definition, is just the mean of the variety minus the overall mean, right? So before we do that, right, just kind of to point out that once we find those means for the different varieties, we can sort of point out to students, see there's some variability in the average firmness from one variety to another. And we see that Selva, right, is pretty hardy, it's pretty firm to start out with, regardless of which treatment has been given, while Vesper is a pretty fragile variety of strawberry. It's not very firm to start out with, right? And so then we can compute these effects. So variety mean minus the overall mean, which was 6.28 newtons here. And so now we get the effect of each variety. And so I would have my students interpret these effects, right? What does it mean for the effect to be positive? What does it mean for that effect to be negative? And then, right, to compute that sum of squares for variety, we're going to sum over the 5 varieties the sample size in each variety times the effect of that variety squared. And so that's kind of what that looks like for the first 2 varieties, All-Star and Bounty. And we come up with 63.51 here is the sum of squares for variety. So then, right, I would have my students sort of put that into the analysis of variance. We've entered another source of explained variation here, the variety or the block. We've talked about degrees of freedom, right? But we're going to enter that 63.51 sum of squares that we computed for variety. And then, right, that, because the total sum of squares, the total variation is a fixed number, that variation due to variety has to come from somewhere, right? And so it comes out of sort of that previous sum of squares error value. And so now, right, we get this new sum of squares error, which is much smaller. We can compute new mean squares, and now we see, right, that we've accounted for a lot of variation just by removing that sum of squares for variety, and so that really blows up that F statistic. And so even, comparing that F statistic to a new F distribution, which will have 2 and 8 degrees of freedom now, it's still highly significant. So I'm going to take you now to the one blocking variable applet. And so let me come over here. And so I'll let somebody maybe chat the link to that applet. So the strawberry data comes preloaded in this applet. And so show you a couple of the bells and whistles here. So we computed the block effects. And so I'm going to turn those block effects on. And so there's those numbers that we computed, right? The effect of each block. And we can show the ANOVA table here. So I haven't done anything with blocks yet. So this is just taking the storage method into account. If we adjust the data for the block effects, then you'll see the sort of updated analysis of variance table, and then sort of the updated partitioning of the variability in the pie chart. But the thing that I really want to show you here is, right, what happens to these firmness values when we adjust for the block effects. And so there's sort of two things that I want you to watch. First, watch the standard deviations here, right? When we adjust the data for the block effects, right? And so what's happening to those standard deviations, right? And so I would want to talk with my students about what it means to adjust the firmness values for the block effects. And so this idea that we are literally going to subtract the effect of selva, for example, from these three data values. And when we do that, because that effect is positive, those blue data values are going to shift to the left, right? And the same thing is going to happen for all-star. When we subtract 1.4 from each of those firmness values, those values are going to move to the left. But because the effect of Vesper and Bounty are negative, if we take this firmness value and we subtract a negative 2.7, this value is actually going to move to the right, right? So when we're adjusting the data for variety, we're literally subtracting the effect of variety from each of those data values, right? And so what that does, right, is it reduces the unexplained variation or the leftover variation, right? That error is going way down, right? And so sometimes this is a little easier to see with the box plots, right? But the box plots are not really meaningful here because we've only got 5 data values in each group. But right, if you turn on the box plots, then right, it becomes super evident if they haven't already kind of gotten it, that within storage method variation is going way down when we take out the effect of variety, right? So now kind of the other interesting thing is watch the means here. So these are the means for the different storage methods. When we adjust for blocks, those means stay the same. And that's because of the orthogonality in the design, right? So we can remove the effect of variety without changing the means for the 3 treatment groups. So I think maybe Beth is going to talk about sort of this adjustment process and in an observational study, we would expect these means to change because of the confounding. But in the designed experiment here, because of the orthogonality, we're not seeing a change in the means. And so that's then reflected down here in the analysis of variance, right? So the sum of squares for the storage method is 11.19. When we adjust for blocks, it stays at 11.19, and that's because it's coming from the means, and the means haven't changed. So, right, we can talk about adjusting, and the only impact that adjusting for blocks has is to reduce that sum of squares error and then give us a more precise F statistic and a small p-value here. So, oh, darn it, that's not what I meant to do. Sorry. One final thing I'll mention here is method 2, right, is that we can account for blocks within the simulation process. So if we're doing simulation-based inference, right, we can account for blocks by re-randomizing using the randomization process that was used in the original study, right? And so by that, then we mean within block randomization. So I'll go back to the applet here and turn on the shuffle options, and you'll see there's a choice between completely randomized shuffling or within block shuffling. And so here I'm going to turn off, let's see, I think that's how I need to do that. So we want to repeat the randomization that was carried out in the original study, which means we actually want to shuffle within blocks, right? And so if we shuffle those responses, we've kind of got a visual for students to be able to see, right, that we're going to shuffle the observed outcome within a block back to a storage method, right? And so sort of letting students see that re-randomization is being done independently within each block. And then we're getting a new F statistic. If we crank this up, right, we can get a distribution of shuffled F statistics, right? But now we need to go back and use the original F statistic, which was 1, and use this simulated distribution, right, to assess the statistical significance of that original F statistic. We don't want to use the block adjusted F statistic because then we're accounting for blocks twice. So we use the original F, shuffle within blocks so that we're getting the correct variation here against which we can compare that observed F. So I'll bring you back here. All right, and then, right, we would sort of adjust to the null and alternative hypotheses here. I would typically include language, after accounting for strawberry variety, and then, have the students provide a conclusion for that p-value, right? So just a quick summary. So in a designed experiment, the idea here is that if possible, right, we can design out a source or sources using blocking. Blocking variables are inherent characteristics of the experimental unit, right? So things like strawberry variety, plot location, participant weight, these are not variables that can be randomized to the experimental unit. They're inherent characteristics of the experimental unit. If we use a block design, then that analysis needs to account for blocks. And then the idea would be to randomize everything else, right? So either by randomly assigning treatments or randomizing things like run order or test order, um, things like that. So I'll stop there, stop sharing. I don't know if there's any questions.
Questions for Karen? Let me ask one, which I think will be a quick one. In the first example you presented, you talked a lot about explained and unexplained variation. And then in the second example, when you got into ANOVA terminology, you were talking about an error term. So my question is, if you got to start statistical terminology from scratch, would you change error to unexplained or something like that? Or
Yeah,
what would you refer to
probably.
it?
Yeah, I think it would. I mean, I think, in a definitely in a first course, I think just staying with unexplained variation, leftover variation after we account for the variable, things like that is great, and then once we get into the second course, because we have the analysis of variance table, and somebody, I guess, smarter than I decided to use the term error, right? So we're sort of wedded to that, but trying to show students, that it's the same thing. But yeah, I probably, if I could do it, would go back to something like unexplained.
Is your sense that students get it quickly that they are the same thing, or do they struggle at
I think
all?
so. Yeah, I think so.
Another question for Karen? Well, it is the top of the hour, so it's a nice time for a 10-minute break. So thank you very much, Karen. We'll hear from Selma Roy 10 minutes from now. Please give yourself a 10-minute break. And next up will be another Cal Poly colleague of mine, Selma Roy, has the next session. So go ahead, Selma.
Thank you, folks, for being here, and thank you, Alan. I'm putting the link for the slides in the chat. So these are the slides I will be using. I'm going to go ahead and share, and we'll get going. So I'm going to basically continue on with what Karen started discussing with design experiments and how we account for additional variables. So a quick recap of some things that Nathan mentioned yesterday, and you saw in some of our discussions yesterday, and then also what Karen mentioned. What we are trying to figure out is what we mean by multivariable thinking. And what we've landed on is that multivariable thinking includes recognizing that variation in a response variable potentially comes from many different sources. If we observe a relationship between two variables, it matters the context in which we observed that relationship. So who the data are about, how the study was done, was it an experiment, was it an observational study, how the study dealt with these other variables that might affect the response. And then lastly, for now, to isolate the effect of any particular explanatory variable that we are interested in, we need to account for the other sources as much as possible. So in Karen's example, if I want to really find out if the storage method matters, I need to kind of separate out and reduce as much of the unexplained variation by accounting for things like variety, by blocking, and other aspects of strawberries themselves by random assignment, randomization of run order, and all that. So to get us warmed up, I'm going to ask you to put in the chat, what do you think, in this example of birth weights, what do you think are some variables that might explain why birth weights of babies vary? So if you were doing a study and you wanted to know why are birth weights different, what kinds of, okay, so is a baby boy, girl assigned, gestational age, gestational time, parents' weight, all right, lots of things, healthcare access, mother's nutrition, if the mother has gestational diabetes, lots of good stuff, how big the parents are, parents' height, weight. All right, awesome. All right, so let's see. So what does the literature say? So I looked up some studies to look at, what people had found. This is a particular one from 2012 that's actually looking at predictors of birth weight of babies among adolescent parents. So these are young parents. And they thought that educational level was important, age at pregnancy was important. They also looked at or a significant predictor, statistically significant predictor. And they also found body mass index. So I think someone mentioned height and weight of parents. That was. Another study looked at a study that was done in Assam, India, which is a northeastern part of India, and they found maternal education, monthly income, whether the birth was preterm, if the mother had low BMI. These were found to be statistically significant. So notice that these contexts are changing, and when the contexts are changing, maybe we kind of want to be careful about the association and to whom we generalize. So again, bringing in those ideas that you saw yesterday. These are studies that you could discuss. These are real world research papers that have been published that could be discussed with a Stat 1 course. And you can say, okay, these associations are being observed, but in this particular context. Here's another one. This was in the European Journal of Clinical Nutrition. This is looking at a Norwegian study, and they found maternal dietary patterns to be a significant predictor. And this one looked at how the ambient temperature during pregnancy might be associated with the birth weight of the baby, and this was in China. So these are all different contexts. These are different studies. And what you've noticed most likely is that these are all observational studies. So we want to, or the example that we'll be looking at is not going to be an observational study. So we'll see what happens there. And we are going to look at designing an experiment. But we now know that when we want to, let's say, investigate what might predict or affect the birth weight of a baby, there are lots of possible sources of variation. So how do we account for all these sources of variation, but specifically in a designed experiment? And something that you saw with Karen's example was, did not want to give that away. So something that you saw in Karen's example was that you wanted to list out all possible sources of variation. Then you block on variables that are inherent to those observational / experimental units. So example was to block on strawberry variety. And strawberry variety is a source of variation that cannot be randomly manipulated by the experimenter. So the researcher blocks on sources that cannot be manipulated or randomly assigned, and randomizes for all other sources, known and unknown. So things like, are these strawberries different in sizes? Are they different in colors to start off with, and so on. All right, so let's actually look at what happens in a designed experiment, how we do those kinds of things in a designed experiment, and along the way, figure out how we're going to account for these multiple variables. Again, as a reminder, we are thinking of accounting for multiple variables. So we were looking earlier at examples of birth weights of human babies. I should have been more specific. I told you just birth weights of babies. I didn't tell you birth weights of what kinds of babies. So now we're actually going to focus on birth weights of baby skinks. So skinks are these, if you don't know or not familiar with the wording, they are these little lizards or reptiles that you kind of can see in gardens and stuff, but they mostly live outdoors. And this particular research study looked at the effects of maternal basking and food quantity during gestation. So that's the pregnancy, how they provide evidence for selective advantage of metrotrophy in a viviparous lizard. So first things first, I was very surprised to learn that a lizard could be viviparous or have babies instead of lay just eggs. So this particular kind of skink that they were looking at actually doesn't lay eggs, it has babies. So that was interesting to me. And in this particular study, they wanted to look at the explanatory variables they were focusing on were maternal basking and food quantity. So Basking means basically laying out in the sun, and food quantity is kind of a measure of food availability. And the response variable here was body mass at birth, so birth weight, and measured in milligrams. All right, so let's switch gears from thinking about babies of humans' birth weights and think about baby skinks. And we want to think about the sources of variation diagram again. We want to know how birth weight varies, the sources of explained variation that we or the researchers are interested in are maternal basking and food quantity. We have all this other stuff to fill in. Um, I invite you to put what you think are some variables besides maternal basking and food quantity that might predict a baby skink's birth weight. So put it in the chat if you will, please. What they eat, so food quantity, how many siblings, size, age. All right. All right, looking good. Captivity, wild, gestational age, season. These are great. Predators nearby, emotional effect. Yeah. Food quality. All right. Thank you. Those are great. So what you did not say were things like education level or income level. So context matters, right? When you think about variables, when you think about any kind of study or what kind of possible variables there are, you won't be accounting for educational level or income level of skinks. All right. So now we have all kinds of things in there. You actually were much more creative than I were. So you had a longer list of sources of unknown variations or unexplained variations, I mean. So all of those things that you suggested, proposed, would go in here for now. So let's take a look at how they did the study. So far we have our sources of explained variation. We have our sources of unexplained variation. Let's see what the researchers did in the study. So what they tell us is that they got 160 female, I can't really pronounce that, but I'll tell you what it means in everyday language in a little bit. And the study was done in Tasmania, Australia, and they tell you what time period shortly after ovulation took place. They also tell us how these females were, or the female skinks were randomly assigned. So they were randomly assigned to 4 different treatment groups in a 2x2 factorial design. If that's not in your Stat 1 course, which it isn't in mine, totally fine. You don't have to worry about that for right now. So if this were a Stat 1 course, you could say, well, here are 4 different groups, and they were assigned to these 4 different groups. The first group was 12 hours of basking opportunity with high food availability. They were given like 3 mealworms per lizard 3 times per week. And they actually looked at what is standard nutrition for them, and their minimum was set to be the low food availability. So they're making sure that these skinks that they are experimenting on are not being like abused food or deprived of food. So they're either giving them the standard requirements or giving them higher than that. And so the first group is 12 hours, lots of sun, lots of food. Second group is lots of sun, less food, but the less food is actually their standard food. 4 hours of basking with high food availability and 4 hours of basking with low food availability. So they have these 2 different things that they're manipulating, but they've set up 4 what we call 4 treatments, and those are the 4 treatments they have listed. So because they're actually randomly assigning, we know that they are not doing an observational study anymore. There are variables that are being manipulated, so it is actually a randomized experiment. I don't think in a human study, you would probably not be able to do this kind of thing, where you're manipulating how much food or sunlight a mom gets. But because this was on skinks, I guess it was okay. And they were being nice to the skinks. So just to be clear. So now what do we have? We have birth weight is still being explained by sun exposure and food availability. So now we have narrowed that down to what sun exposure or maternal basking and food quantity means. We've also talked about, okay, so those particular skinks are called southern grass skinks. They were from Tasmania, Australia. They were female skinks with ovulated follicles, so they explain all of that. But we still have some unexplained sources of variation or things that we haven't been able to track. So we are going to use random assignment to make sure, like Karen said, random assignment will try to at least spread out the effects of these other sources of variation among the 4 treatment groups evenly. All right, so we're going to now switch gears and get our hands dirty with the data. So if you have the link, you will be able to get to the multiple variables applet. And then before you go there, though, I would also make sure you know that there is the skinks data available and it's in a Google sheet. So I'm going to open the skinks data. And there's my skinks data. Let's see, do I have a question? All right. So here's my skinks data. There are the 160 skinks data weights available. I'm going to copy all of that. So, whoops. And when I share Google Sheets with students in class, I actually just, I always set it to view only. So I don't end up, or they don't end up messing up my data set for any reason. And we are going to go. Nope, not that. Go back to my. That's my. All right. So this is one more applet from the Rossman Chance applet collections. This is called multiple variables. Data just like Karen did before to update the variables that are available for me in the model. Check the. All right. All right. So first thing I'm going to do is I'm going to just see what if I just I'm going to because birth weight is my response variable. Drop birth weight in it. So I can see some descriptive statistics. About 170.11 was the milligrams was the average birth weight of these baby skinks, and the standard deviation about 29.51. And then I want to, so here's the setup. I want to account for food availability. So I'm going to go ahead and drag food availability on subset by. I can put it in explanatory as well. I just like to see this first. So I've put in birth weight, food availability, subset by, and I can see 2 different graphs. Skinks who had low availability and high availability of food, what their mothers had during gestation. And you can see that the average birth weights look a little bit different for babies whose moms had high availability of food versus low availability of food. Okay. Okay. Go back for a second here. I'm going to go back to my slides for now. So here's these show descriptives. You can also get the analysis of variance table that Karen was showing, and also an accompanying pie chart that shows you how that sums of squares was split. So, whoops, not that. What is that? Oh, never mind. Yeah, you did not want to see. Okay, I'm I'm going to go back to my applet this way. Okay. So if I scroll back down, you can see under, this is the applet that we have. We are going to check on ANOVA table, and it shows you how the sums of squares, total sums of squares, that was 138,000 plus, has split up into two pieces. One piece, the explained variation, is the food availability, and the unexplained variation is that 115,000. And it's showing you that food availability is a significant source. So you can do this and kind of, tell students, yeah, it looks like the difference between skinks whose moms had high food availability and moms who had low food availability, the difference in the birth weights of these babies is significantly different, or is statistically significant. Okay, so there is that. You could do the same kind of thing if you wanted to just do a one variable ANOVA, you can do the same kind of thing with basking time. So here's, you just account for basking time in your analysis, and the sums of squares again get split up into explained and unexplained variation, and you can find a predicted equation. And so this is something I think is fine for a Stat 1 course to do. If I want to just think about how far can I push with this for a Stat 1 course. So Stat 1, they actually could have just done a two-sample t-test here because there's only two groups, high basking and low basking, or long basking and short basking times. You can look at those two means and you can kind of come up with a prediction equation saying, oh, predicted birth weight is going to be about 177.6 if basking time is 12, 162 if it's low, and so on. So you could look at both of those two analyses or two variables separately, food availability and basking time, and kind of make these equations. But you can also ask them, well, this was one study and these reptiles or these skinks were given combinations of these. So why don't we account for both variables in the same analysis? And one way to do that would just be to do a one variable ANOVA or one variable analysis of variance with 4 levels, where you have, instead of looking at basking time and food availability separately, you just have this one treatment. And the treatments levels are those 4 that the researchers had set up. And if we do that, we can see again that there are differences in these 4 groups. And you can kind of see that, the high basking, high food availability had the highest mean birth weight. Okay. You can keep going and you can kind of pull the treatment into the explanatory part and generate an analysis of variance table. So you can see that sums of squares is actually higher than what it used to be for just the basking time or food availability separately. You see how this has split up. So now you're explaining a significantly higher fraction. So the dark blue wedge in this pie chart is bigger than it used to be for just food or just basking. And you can actually come up with another prediction equation again. You can say, well, I can now write out a more detailed prediction equation. I can say predicted birth weight can be this if it's this combination, this if it's this combination, and so on. So I would argue that it is fine to do this in a Stat 1 course where you're trying to show them how multiple variables have been taken into account at the same time. But what is the disadvantage? So if I were to present that particular approach and tell students, you know what, this is one way to do it, but there are other ways to do this. And kind of tell them, a coming attraction for Stat 2 would be something. What do you think I can pose as a disadvantage of approach 1, this way of doing things? It's good for now, but what is it lacking? You can put it in the chat if you like. There's no interactions. Okay. So my students don't know no interaction yet. So let's say in Stat 1, I haven't mentioned the word interactions yet. So they don't really know that word. What else do you think they might say? Doesn't account for how the categories are related to each other. Perhaps. What else? So what does this equation say? Can't say things like low is always worse, all right? So you can't really separate out the effects of basking and food. And I think that's the big disadvantage of approach one. So even though approach one is nicer than just looking at one variable at a time, looking at this one equation that has these four different predictions for four combinations doesn't let me separate out the effects of food availability versus the basking. So what can I do? Maybe I can do a different approach. So let's see what happens if I do a two-variable ANOVA or a two-variable analysis. So we're going to do something similar to what we've done before, and I'm going to go back to my applet, and we'll probably have a little bit of so here's how I'm going to set it up. Instead of putting treatment in my explanatory, I'm going to put basking time and food availability in my explanatory. All right. So here we go. I'm going to remove food, put it under explanatory, take basking time, put it under explanatory. And now I can see that I have kind of, split up this entire SS total, sums of squares total. There's a piece that's because of basking time. There is a piece that's says previous because food availability is down here. So it's adjusting for food availability. So this is for basking time. The green portion and the darker blue portion is the portion of variability that's explained by food availability. You can see the same kind of information down below in my analysis of variance table. Okay. You can also look at the plot up here. It's kind of showing you how the basking time and food availability combinations are working. So essentially here it's saying, okay, if you have 12 hours basking time and high food availability, that's the red, those are the red dots. And here are the blue, the red dots for high food availability, but 4 hours. I can ask it to show equations. So it's going to show me an unadjusted equation first, and it's going to also show me separate equations for both. So if I have low basking time versus low food availability versus high food availability, I'm predicting two separate equations, one for low food availability, one for high food availability, but showing you the effect of basking time within each within each category of food availability. Take a look at this. Beth's asking if the SS values are the same. Yeah, we'll come to that. It's a good question. So the two variable ANOVA, this is a picture that we got, and we can get the same sort of ANOVA analysis of variance table set up. Here is the SS total output. Here are the equations that we saw. Here, actually, I switched the order of which I entered first, so now it's showing you separate equations. But what's the notable feature in these two equations? What's same? What's different? I'll let you chat. You can tell me between these two equations, the red and the blue, what's the same, what's different? The slopes are the same, right? And the intercepts are different. Can you tell me why the intercepts are different, or where we might have seen the different intercepts before? What are these intercepts? So this is something I might ask students if they can tell where these intercepts are coming from. They are the means for something. Actually, in this case, they are the means for the basking. That's right. So they are the original means for 4 hours basking and 12 hours basking, and then they're getting kind of adjusted based on food availability. When you want to predict the birth weight, they're saying, okay, well, depending on food availability, I'm going to adjust that prediction by 11.91, either subtract or add. And as you pointed out, these are the same because in that graph, we saw that these are kind of just fitting parallel lines. And that might or might not be a great idea, the fitting of parallel lines or keeping these the same amount. And we're going to see what happens then. So we're going to compare some things. And I think here are the parallel lines that we were talking about earlier. Let's actually compare and contrast what's happened between the two approaches. We will get to Beth's question about how the sums of squares are same or different from the original one variable ones. But let's take a look at what's happening here with approach 2 versus approach 1. So remember, in approach 2, we've put in basking time and food availability separately. So the positive of that is now we can account for the two separate variables, and we can see how much of this variability is coming from basking time, how much of this variability is coming from food availability. And, we can see that food availability actually is explaining a lot more than basking time is. So compared to approach 1, where all of that was clumped together, have we done better? Yes, we have done better. We have kind of done, it's one problem with approach 1 that got taken care of. Are we happy with approach 2, though? Are we satisfied? Would I be happily able to turn off my computer and go to bed? If not, why not? I'm telling you, no, I'm not happy. Why am I not happy? What is something in the output that's signaling that I shouldn't be happy? Let's see. SS model is smaller with approach 2. That's right. SS model is smaller with approach 2. SS error is larger with model 2 or approach 2, right? Yeah, exactly. So the unexplained variation is actually bigger in model 2 or in approach 2, even though we kind of try to kind of separate out the effects. So what have we not done here? We need to actually the SS model has gotten smaller with approach 2. The SS error has gotten bigger with approach 2. So we don't like approach 2 as much yet. In some sense, maybe approach 1 was doing better. So what should we, and I think somebody already talked about this earlier. So what have we not done with approach 2 that we could do? How can we build on approach 2? Oh, interaction effect. All right, you're reading my mind. So if you thought that we need to put in an interaction of basking time and food availability, you were exactly right. So what we're going to do is we're going to take that previous sources of variation diagram that we have, and we're going to add in an interaction of sun exposure and food availability. And like Karen said, every time we put something in this explained variation column, we're taking it out of the unexplained. So that means that we're probably going to start reducing that SS error again. So let's see what happens if we do try to do that. And how we do that with our applet is we're going to put one of the explanatory variables in the explanatory variable column or the box, and the other one in the subset by. Okay, so move over to my applet. Oops, that's not this one. And instead of having both of them in the explanatory, the way we're going to allow for the interaction is we are going to drag one of them. And I forget which one I had in there. So I'm going to quickly look. I put basking time in there so I can match my output. And doing that allows you to have these non-parallel lines or allows for that interaction. So your equation should update up here and your ANOVA table should update as well, which now shows you an interaction term. All right. So let's take a look. So there's your updated graph, tables, the SS total, still the same, but now less of SS error. And I think someone pointed out there is still a lot of unexplained variation. There is actually in this study. And even like, the researchers only actually accounted for food availability and basking time. So in this particular study, there is a lot of unexplained variation, even after accounting for these other sources. However, even though there is less unexplained variation, there is a lot of unexplained variation, beg your pardon, the sources are statistically significant. And some of this is not surprising because the sample size was pretty large in this study. So now notice that the model sums of squares actually matches the approach one sums of squares, and the error sums of squares matches the approach one sums of squares. So what that one variable for treatment analysis, approach one, was doing, approach two is doing exactly that. But in addition, it's also letting us or allowing us to look at the effect of each of these factors separately, instead of clumping them all in that one variable. So that's the beauty of having this factorial treatment structure, is that it allows you to look at these separate sources separately and have their own individual sums of squares. Notice that this interaction sums of squares that we have, that is exactly the amount by which the model sums of squares was lacking in approach 2 originally compared to approach 1. So this interaction sums of squares has come out from that error sums of squares, and Karen talked about it. And I'm going to show you a picture in a little bit about how every time you put in a well-designed experiment, every time you put in additional variables up in your model, the sums of squares for those get pulled out of the SS error. So the more variables you put in your explained sources, the fewer you have in your unexplained sources, and the fewer you have in your unexplained sources, the smaller your SS error is going to be. All right. We can also do these equations as before. So you can say, okay, well, you can have two separate equations, one for the 4 hours of basking, one for 12 hours of basking. And now, because you're allowing that interaction term, notice that the amount of change that's accounted for by food availability is actually changing from one equation to the other. So it seems like if there are 12 hours of basking, there is a bigger difference between high and low food availability than if it was 4 hours of basking. All right. So how the effects get updated. So you'll notice something similar. So originally in the original data, without accounting for any kind of food or maternal basking, the average birth weight was 170. When I accounted for just basking time, I took that 170 and I said, okay, well, depending on if you're basking for a longer or shorter period of time, you would adjust that amount, adjust birth weight by 7.52. If I account for food availability, I'm going to take the means for the basking times and then adjust by some increment depending on food availability. This is without any interaction. And that equation then gets updated to, as soon as you account for two variables, depending on whether you are including an interaction or not, this slope term changes. So if there is an interaction, the slope term will change. If there is no interaction, the slope term won't change. But what's similar is that these first two equations both have that 170 is getting adjusted. And the second two sets of equations have the 162 and the 177 the same, but the effect of food availability is getting estimated differently depending on whether there is an interaction or not. Similar things happen with regard to the sums of squares total. So sums of squares total, yeah, the variables work together. So the sums of squares total the 138,000, that actually is a version or some form of the variance basically of our response variable. So this is our note to ourselves that this standard deviation, this 29.51 that we see, this is actually what is used to calculate the SS total. And originally, with no explanatory variables in our data, all of that is unexplained variation. When we go to just one source of variation or one source of variability, that 138,000 gets split into these two pieces, one piece due to food availability and the other piece due to error or unexplained variation. If we throw in basking time as well, and this is the question that Beth was asking, what happens to the sums of squares? So notice that the food availability sums of squares actually stays the same. So this error sums of squares gets smaller, and it gets smaller by how much ever the basking time sums of squares is. And if I include the interaction term, again, the original two sums of squares, the basking time and food availability, stay the same. This interaction sums of squares gets pulled out of the error sums of squares. All right. Why does this happen? It happens because in design experiments, we have this wonderful setup where the different factors, and if you design an experiment well, you'll have this property of orthogonality, meaning whatever information food availability provides for you is totally independent of what basking time is providing for you with regard to how much variation they're explaining in birth weight. So they are giving you like these separate pieces of information, basically. And this particular feature of design experiments is what is very, very attractive, because then it kind of, you don't have to worry about adjusting for or accounting for really in the observational studies sense. I saw that Andrew asked a question about the indicator versus effect parameterization. So the applet actually does have that. So let's see if I can find that for you. Sorry. So, wrong one. So down below here, you can actually choose indicator or effect coding, if that answers your question for them, for that. And do students, I actually don't in the stat 2 course, I probably might go over it very quickly, but for stat 3 or my design experiments code, I might go into it more in detail. And Andrew, I'm not sure if I'm answering your question, but they can kind of, at least in a design experiment, that's what I would do. And maybe I can come back to it and you can ask me in the Q&A or something. All right. Okay, so that was about, sorry. So that's how the SS total gets partitioned. In terms of how the effects get updated, so we talked about this a little bit before already with the equations, but let's take another quick look. So if I use my statistical model setup down below, so notice how in the beginning there was 170. And then when you accounted for food availability, you took that 170 and you said, well, if you have low food availability, you will subtract that from your average weight. If you have high food availability, you will add that to your average weight. And I really like how the applet actually gives you all the estimates instead of just one. Like I think most software just give you that one particular, and then you have to figure out what the other one might be. And that students sometimes don't like that. But that's a separate issue. If I include basking time, notice that the effect of food availability, those coefficients did not change. All it did was said, okay, well, you have that set up already. I'm going to include also what happens if you were to change basking time from 4 to 12 hours or 12 to 4 hours. And then, well, if you have an interaction, again, those other two effects didn't change. All that changed was what is the additional effect of a combination of low N4 or high N4 and so on. So I really like to show this to students to kind of drive home the point that in a design experiment, these things, when like in usual regression equations for observational studies, we'll say, okay, you need to say after adjusting for when we interpret the effects. But in a design experiment, we don't really need to do that because the design of the experiment adjusts for the effects. Yes, you do need to think about adjusting when you're looking at the statistical significance, but the effects are already adjusted because you designed the experiment well. Some other questions to think about or student questions to anticipate. Is this analysis different from when we analyzed the randomized complete block design in the strawberry study? Would I do anything differently in the applet? Not really, except in the strawberry analysis, you don't really have the interaction because in an RCBD or a randomized complete block design, you don't have that replication of combinations of variety and storage method. So you don't have an interaction term. Sometimes students also ask, well, is the study design different from when we had? So sure, the analysis you're saying is not different, just we can't include an interaction, but is the design of the study different? And I like to say, yes, it is different from an RCBD because even though both of these studies have those two factors under the explained variation, so they kind of have the strawberry study had variety and it had storage method. This particular study has the basking time and food availability. In this particular study, they manipulated both the basking time and food availability. In the strawberry design, they couldn't manipulate the variety. The variety of a strawberry is what it is. So we do need to think about when something can be manipulated and then thus be randomly assigned versus when something is not able to be manipulated and so it should be a blocking variable. I think that's it for me for now. If you have questions, which I think there's stuff in the chat, so I'll look at that. But here are some of the links for stuff. All of these, this entire slide deck and everything that you need is basically self-contained in this, is on our project page, and I'll share the link or someone will share the link again with you. Okay, so I'll stop and
questions for Soma that weren't already addressed through the chat?
I'll stop sharing, so I stop this. I guess I should ask, what was if you have a skink and you wanted to have big babies, what should you do? I guess I usually ask this at the end of my class. Should let them bask a lot and also give them a lot of food, or at least have it available. I don't know if they're eating all of it, but they're having it available, I guess, like cats.
Questions for Soma? How about if we take a 10-minute break now? It's 4 minutes till the top of the hour by my computer. Let's go until 6 minutes after the top of the hour. Give yourself a 10-minute break. Beth Chance will present our third and final session starting in 10 minutes. Next up will be Beth Chance, who is another colleague at the statistics department at Cal Poly in San Luis Obispo. Take it away, Beth, please.
Thank you. Actually, there's a great question in the chat. I'm assuming for Soma. Do you want to address that first?
The multivariable thinking question?
Yeah.
Well, some aspects of it I mean, many of these questions are or things that I've brought up are not new and they have worked, although like, I haven't documented it in any way other than student doing fine on exam questions on assignments and stuff. But asking about confounding variables and both Stat 1 and Stat 2 type of courses, even like my design of experiments course that I teach, I think we've done all of these things about, list out the sources of variation. How are you gonna account? Projects are a good way to assess that too. So I've done that too. So um, if me reading good written reports and good student answers is a measure of how successful the class is, I think the asynchronous online environment was fine with much of these approaches that we've discussed yesterday and today. Does that answer your question, Brett? I think Laura also has some asynchronous online stuff that Laura does, right? So maybe she can answer that too. There you go.
Well, and a little bit related. So what I think I have left to talk about today, and thank you for sticking with us on the end of day 2 here, is things don't always work out quite so nicely with observational studies, but we still want to make a lot of the same interpretations. And we still want to consider that there's lots of sources of variation. And how do we focus on a comparison of interest, even when you have all these other sources of variation? What happens when you can't block or randomize to groups like in an observational study? Can you still do adjustment? Can you still talk about interaction? And I'm going to focus on 2 maybe less interesting data sets today, but just to show you some of the things that you can start with and what you can talk about, and we'll give you links for those as we go along. And I'm also going to try and demo some maybe new features to the applets that we're trying to do, partly to make it easier for students to get these visuals, to focus on the statistical thinking, and to not get as bogged down in some of the technical details. And I think that's especially important in an asynchronous environment. We want them to feel comfortable playing, trying things, making observations, and not struggling with the technology. And so we're especially looking for feedback on some of these features to see if you think we are accomplishing those goals. And I think you've seen some demonstrations of how we just try and make it much more visual and have much less of a focus on the calculations, or even what calculations we're doing are adding and subtracting to talk about effects and how we interpret those, and not getting into, as Nathan was mentioning yesterday, a lot of the, linear algebra or multiple regression details. So I did put you can get a copy of these slides and a copy of the handout, and I'll also be going through this handout a little bit in the EA Post website. And so the first thing I want to talk about is this real estate data from Kaggle, and I do have a link that we can share with you for this data set. I actually have been using a self-made link because Kaggle now you have to kind of log in. It's still free, and there's a lot of data sets there. You'll see this is a little bit older, but I was just looking for real estate data. I do still have to be a little careful because I wanted to show something very specific, so I had to look at several different data sets before I found the one I want. But this is just going to be data trying to predict housing prices in this particular county. And so I'm going to do something that the other instructors have been doing as far as ask you to first predict what are some things that you think might influence or some potential sources of variation in housing prices. One thing I'll add to that now is also think about whether you think it's going to be a positive association or negative association. So I'm going to focus a lot now on quantitative variables. So be thinking about if this variable goes up, do you think the house price is going to go up or go down? So go ahead and share some ideas in the chat, and I'll demo something I did in class. And sometimes I do these for recordings for students too, as far as just sharing what people are answering. And then I save this as a PDF and I make it available to students later. And that's how I kind of provide them for solutions, or you can have students share their own notes, just a way to kind of to share that. Solar panels, you would need to think about, how are you going to make that a numeric variable? Yes, no. And then does having solar panels raise the price? Same with location. How are you going to put that into maybe a regression model as a numeric variable? How many categories are you going to have? Size of the house would be a nice quantitative variable. So that's often measures in just kind of square footage. Distance to schools, maybe quality of the schools, age of the home would be another nice one. That one you might expect maybe once it gets so old, it starts to become historic, and that might change the price. So it's maybe a negative association up to some point, but I might want to consider a nonlinear relationship with that as well. And then size of home is also different from the size of the lot. So maybe that's what acreage means, some things like that. So if you look at this Kaggle data set, and I should have a version here. They also had number of bedrooms, number of bathrooms, number of floors, year it was built, and year it was renovated. And notice how that means 0 if it wasn't renovated versus a numerical value. And so that's something you'll have to think about as well. So I'm going to put this data into the multiple variables applet, and I'm going to try and put it in what I'm going to call a test version of the multiple variables applet. Actually, I'm lying. I'm going to put it into the 2 quantitative variables applet. But again, I'm putting it in kind of a test version of that. So let me paste this here. Let me paste this over here. So we're all maybe in the same applet. But notice what I did is I just pasted the URL, and that's a new feature that sometimes works. And this is a big data set, so do give it a second before we give up on whether it's working. We do try and make this, turn colors, so you might know there's more to do. What should be happening here is you should be getting a preview of the data coming from that URL. Sometimes it makes a difference whether you're using HTTP or HTTPS, but I thought I changed that last night. So we'll see. And fallouts, fails, you can always go back to the data set. You can select it all, copy it, and then paste that into the applet. And that's usually how we have students enter data, and you can do this with tab delimitation or comma delimitation. So now I do see the preview of the data, so then I press use data and it pops up in here. And so we've been trying to make these applets a little bit more flexible. You don't have to only have 2 quantitative variables. It's going to now allow me to select from a list, and it's going to give me the quantitative variables that I can select from. And I'm going to scroll down a little bit. I'm going to look at correlation coefficient. And then if I go back here and just kind of highlight this again, I'm just using the down arrow, and I can just scroll through different variables. And so I can quickly answer questions like which one had the highest correlation coefficient, which one seemed to be the most strongly related to the price. And then also ask questions like, do I want to remove any observations like this one over here, or at least investigate what home has over 30 bedrooms in that county? And just thinking about, do I need to worry about some of that nonlinear behavior? The most strongly related seems to be price versus square footage. Let me ask you in the chat, are there anything about this data set that would bother you as far as fitting a regression line? Non-constant variance, and so this is a nice example. Still got some crazy outliers as well. So thinking about how you might want to handle that non-constant variance, maybe talk a little bit about why it matters. As far as fitting a line, it may not matter too much, but once I start to make predictions, I need to realize that my predicted price is going to be much less precise with the larger homes than maybe it is with the smaller homes. And I maybe don't want to assume that that's the same all the way across. But also I wanted to well, there's the problem. This is not the test version of the apple that I wanted, but that's the one that I pasted in. Which one did I give you last night, Alan?
I'll paste the one you sent to me into the chat now.
Oh, that's why. All right. So actually, I can't resist. I want to go back and show that taking the URL works. So yeah, we are using you as guinea pigs, and then we'll move these over to the main website once we decide they're good enough to go. All right, so there we got our preview just based on the URL. There we got our data. I'm back to price by square footage. And now I have this ability to play with some different transformations. Again, just trying to make it super easy on students to just try things out and explore and see what happens. One thing that happens here I really like is you get both the relationships. So we're trying to make this one look linear, but what is the implication of that with the original relationship? And realizing that you may not always have this constant rate of change, but the price may increase at a much faster rate as you increase the square footage. Or if your only problem it was the non-constant variance, you might want to do a similar transformation on both. You get your constant variance here. But this is maybe not the best model here because you have so many homes down here that you're still getting some strange behavior. You still have some outliers, right? So I just wanted to kind of think for a little bit about some of those data processing issues, remembering to kind of start there, think about the context, think about the graphs, right? Always start with graphs, but make it easy for students to play and to explore and to bring in their own thoughts and opinions. And then I think it is worth once or twice or a lot, and maybe not every day, but spending that time on pre-processing the data, thinking about outliers, thinking about scaling. Like even here, if I want to start interpreting slopes, let me just go back to the non-transform version. My students get distracted when I say, oh, 1 square foot, my numbers are cut off here. These are just big numbers. Maybe I'd rather divide things through by 1,000. And then just not always doing that and giving students these really clean data sets, but involving them in that process as well. So I could rescale the variables. I can think about transformations as long as that's, not distracting. It's just something that they're looking at and comparing. And then also the idea of filtering and subsetting data sets. So I don't mind them going to the web and maybe copying and pasting this into Excel first and doing some of that data manipulation before they bring it into the applet. And that used to be a lot harder for our students, but that's not something they struggle with as much as more anymore. And so I think it's important to give them that kind of ownership of the data as well. One disadvantage to the applets over, say, a scripting language like ours, I don't have that reproducible code of here's all the things I did to the data set. I can go into the applet and I can just say, I don't like that observation. I'm going to highlight it. I'm going to get rid of it, right? But there's not a good kind of record of that. And so I think it's important to, again, have that discussion of students of why that's so important and teaching them those skills of how to document their experience with the data so that it could be reproducible by somebody else. And those are just some new skills I think we need as we make the technology so much easier for them to do these things. They need to be able to keep track of what they're doing. All right. So now I'm going to switch to my main example today, which is an article I found recently that was looking at, this is my simplified version of the explanation. So there's this part of your brain that gets smaller with age, and that may be related to things like Alzheimer and just your ability to form memories and remember things from the past. And so we want to kind of think about that region of the brain. They actually measure that using these MRI scans. And while this context may not be as immediately relevant to students, and I don't totally understand all the details, they love looking at these pictures and thinking about brain scans and how we're measuring things in the brains. So students may believe that fitness can be positively correlated with MTL thickness. It's really about the hippocampal volume, but again, just kind of simplifying things. I want this part of my brain to be bigger. Exercise might help with that. But this particular article said, we don't know as much about sedentary behavior, and that may be a different issue than just your level of aerobic fitness. And so that was the motivation for this article a few years ago. And so they measured people's physical activity using this questionnaire. And so you can talk a little bit about that and some of the questions on it. And one of the questions on it was also the number of hours they spent sitting, kind of average per day over the course of a week. And we talk about how that was measured over the last week and issues with recall and how accurate these measurements are. But those are going to be the main things that we're looking for. I do encourage you to take a look at this article because it's actually pretty good and pretty accessible. It gets into a little bit more details. They're actually looking at several different regions of the brain, but we're going to total them all up as the MTL. It's got some nice, figures and explanations. And actually the best part is if you scroll to the bottom, it gives you the raw data. Right? It gives you the actual data from the study and you can reproduce the results that are given in the data except for BMI. For some reason, BMI is not in here, right? But you'll see things like ethnicity, education. These are the different regions of the brain, age. Total ends up being when you sub these subregions up, sum them up, you get a total reading, and then sitting. And then this MET, and they explain it again here in the article, was this equivalent amount of time minutes per week of activity. And then they also classified that as low versus high. I think the cutoff was 1,500. Right. So again, students can get into that. You can ask them to read the article. You can ask them to think about what parts they do and don't understand. But a lot of it is actually accessible to them. And so I really appreciated finding that. And so I downloaded the data as this S1 table as it came from the article. And so there's a link for that. And then I went and made a new sheet, which just had a subset of the variables. The article also looked at some of those log transformations. I ended up not really doing that. I didn't think it was all that necessary. It doesn't necessarily hurt. And then I got rid of all the other brain regions, and then I'm just going to focus on this total column. So again, I can just highlight all these columns and copy and paste them into an applet. So because I have several variables, now I'm going to go into what Soma was showing you is that multiple variables applet. Again, I'm going to try and take you to a test version. So I think that's going to appear in the chat. It's got multreg test in here in the URL, and I'll show you a couple new features. So I'm just pasting the data in, press use data, and we're going to be in that drag drop format as we saw before. So we can start with total. Another thing maybe I should have done in Excel is just rename some of these columns so they make a little bit more sense. So that's also a decision to think about. Keep it realistic, but make sure they're not being too distracted by not knowing what's in here. And one new feature to the applet, in addition to box plots, you can now get a violin plot. So there's some discussion about how that helps show the density of the distribution a little bit better than just a box plot would. I find even my college students can make some common mistakes in interpreting box plots, even my stats majors. So maybe showing them some different types of graphs, or again, giving them those options. And now I'm totally off script. So let me go back to what I wanted to do in here. All right. So sources of variation diagram. We've done that a few times. So now I'm thinking about this kind of brain size, and we've talked a little bit about what the researchers suspected might be some variables that are related to brain size of this particular region. Anything else that you can think about? What might explain some of this variation? Why doesn't everybody have the same brain size? And this one's cheating a little bit because you see a little bit in the data set, but what else do you think? Or tell me some things you see in the data set that you'd like to explore. So we have a sex variable in here, gender, age, we've been told is important, and that's definitely something we're going to want to take into account. Body size, like I was saying, I was missing that BMI variable. Race, we do have an ethnicity variable in here. There's actually education in here as well. I don't remember what the E4 thing was, but that might have been some kind of environmental thing. Yeah, there could be other things they didn't measure, like smoking status, and that you have lots of options there as far as how long they've been smoking or when they started smoking and how that might be related to their brain development. All right, let's go back to age a little bit. And let's think about this inclusion criteria. So, I try and give students hints up here. And sometimes I even just say, read this before you come to class, or I ask them questions on this before they come to class. So they're ready to discuss it right away. Is there anything in this description that we haven't talked about yet that you think might be important? And where would it go in our graph, in our table? Mental health. So they did give them this kind of depression or anxiety measurement, and they did remove people that maybe were higher on those scales as being not part of their study group. And so again, that would be important to document. Where are you going to document that? Inclusion criteria, yeah. And also the age, we're focused on older adults here, so 45 to 75, and that's going to be interesting and something that surprised me later that we'll get to. Any other questions on this study? Nutrition, we don't have any information about, but they are supposed to be, reasonably healthy adults, somehow similar that way. All right. And then there's a little bit of information. And again, this is something that I felt was straight from the article to give it that authenticity to the students, but something that they could digest as far as how they measured this level of activity and in the sitting variable. And then just like we did, give them the data and load it into the applet. So let's answer some of those questions. So does lower levels of physical activity appear to be associated with this smaller volume or smaller thickness? So my MET min per week is my level of activity, and we actually don't see much of a relationship with that. So that's actually kind of interesting and different from what they expected to see. And so I can look at things like the correlation coefficient, R squared, our table. This should all be, they can interpret these the same ways they've done before. My model is not doing much to tell me about this particular response variable. But let's try sitting. And that actually explains a little bit more variation. So that's now almost 16% of the variability. I get a correlation coefficient of minus 0.4. And so they kind of suspected this, that sitting might be actually an even more important variable than the level of activity. And I think it's worth asking students to interpret that a little bit. Sorry, I went away. Like, what does that mean? How do you make sense of that? Or what might be true about sitting and just overall, like, how could you summarize that relationship? Like, what does that tell you? Or let me ask you the easier question, and this is the one I would pose to students, is which of these two variables do you think we should be using now? If we want to predict this brain volume, would I rather know their sedentary behavior, how much time they spend sitting, or would I rather know their level of activity over the course of the week? Is it more important that they're physically active or how much they sit? Yeah, sitting seems to be the more important variable. And so a consequence of that is maybe all these studies that just focused on level of activity were missing that important variable. Or, and it seems to be possible to be an active person, but to still have very high levels of sitting, and that those might be explaining different kinds of variation. And if we put them both in the model, and one thing you can do is kind of look at this coefficient of sitting, and let's put the other variable in the model. Let's look at our statistical model. Right? That coefficient's not changing, right? These two variables seem to be kind of explaining different variation. And we'll get to that a little bit more in a minute. But I think here you can even start to talk about this idea of the level of exercise as being kind of independent information, or predicts different things about the brain volume than the sedentary behavior. And so it's important to think about both those variables. All right, so let's think about that adjustment a little bit. In particular, I need to adjust for age. We know age is an important variable, but we haven't blocked on age. We can't randomize age. So how do we account for that? And then make sure that even, if older people tend to be the ones who are sitting more or less, then maybe that's explaining. And somebody mentioned in the chat this idea of proxy variable. Is sitting really telling me about age? And so if I take into account age, and what that means, maybe I'll get a different relationship. So what we're going to do in the applet is we're going to take out our level of exercise, and we're going to put age in here, and we're going to put it at the top. So I'm still looking at the relationship between the brain volume and the sitting, but I'm color coding by age. So the blue and the white, these are the older people, and then the darker colors are the younger people. And so you can kind of see maybe a little relationship there. You can also in the applet check the show two variable graphs if you want to kind of look at this all at once. And so that allows you to see what is this relationship between sitting and age, as well as the age and the total. And this is the one that surprised me a little bit. This is actually a bit of a positive association. So the older people tend to have the larger brain volumes. But maybe that's because of this restriction on the age range. Maybe if I was comparing younger, or especially if I went into teens and early 20s, right, maybe I'll see much smaller brain volume there. And that once you get to a certain age and people's brains have stopped developing, then you don't see this effect of age beyond that. So we do have this little bit of a positive association. And then we have a little bit of a negative association between sitting and age. And that's the big issue here. In the previous examples, session 1, session 2, because you were setting up the experiment and you were doing a well-designed experiment, you got that orthogonality or independence, whatever you want to call it, between your explanatory variables. And so you could take out that variation from one variable without impacting basically the relationship with the other variable at all. That's not what's going to happen now. Now, if I try and kind of adjust for age, it has that relationship with sitting as well. And so there's a couple ways you can think about this. One thing you could do is if you only looked at, say, the yellow dots, what kind of relationship would you see between total and sitting? So if I have people the same age, what does that relationship look like? Or maybe go to your white and blue dots, people of the same age, what does that relationship between brain volume and sitting look like? And does it look different from this overall relationship back when these were all black dots? How does that change? And so let's maybe think about the handout a little bit here. So the association between total and age is actually slightly positive. We saw that from the 2-variable graph. And then we also saw a relationship between sitting and age, which was negative. And so I did mean to give you one kind of joke a little bit. These are some more things from the article back to this idea of independence. But I like that idea of having students look at several 2-variable graphs and then thinking about which one has a stronger association, like which would be the better predictor variable. And there's a nice follow-up question assessment you can have them do where maybe they look at data on earnings from the PGA and they could see who earns more, the people that have the longer drives or the people who are better putters. And you can kind of think of those as different potential explanatory variables and think about which one explains more of the variation in earnings. And the adage is that putting is actually more important than driving, even though driving gets more oohs and ahs. But I wanted to put that analogy in your head because I want to think about this idea of adjusting for the other variable. And so what I want to do is if I go back to that relationship between the brain volume and the age, I want to remove that association with age. I want to kind of take it out. I want to get rid of that effect. And if you go back to those equations that Karen was showing, especially, I have the brain volume is equal to age plus some other variables. And so I want to kind of move age over to the left-hand side. I want to adjust for age. I want to subtract off the age effects. And so what I'm going to do is I'm going to think about raising the brain volume for the younger people in this study, but lowering the brain volume of the older people in this study. And so that's going to shift those dots a little bit and it's going to remove that association. And so if I do that in the applet, I'm going to adjust the Y values. And so you can kind of see that shifting a little bit. They don't shift a lot, but you can see that the older ones went up a little bit, the younger ones went down a little bit. Right? And you're seeing that vertical change. If I was to look at this age-adjusted relationship with age, I should see no association. And so I've changed the variable label here to be age-adjusted. But it turns out what really matters here, and something we do try and emphasize with students when we first talk about confounding variables, it's actually the relationship between the explanatory variables that really matters. And so I need to think about adjusting the sitting for the age variable as well. So I need to adjust kind of both variables for age. And so I'm going to kind of do that same logic because I had this negative association to kind of get rid of that association. When I want to look at the 50-year-olds, I want to lower their values for sitting. And when I want to look at the 70-year-olds, I want to raise their value for sitting. So now if you can transport that the other way to the graph, it's going to move them left and right, right? And so this is what we would now call the adjusted association. between the brain volume and the level of sitting. And this is sometimes called a partial correlation coefficient, right? This is now the association between the brain volume and the sitting if I've adjusted for age. So it's kind of like adjusting for par. I'm putting everybody on the same playing field in terms of age, and then I'm seeing what association is left over between the brain volume and the sitting. Another way you can create this graph is you can do the regression on age. You can do this regression, get those residuals. So what variability in brain volume hasn't been explained by age? You could do the regression of sitting on age. What components of the sitting variable are separate from what I already know based on their age? And are those related to each other, right? Does the part of sitting not related to age have anything to tell me about the part of brain volume that's not related to age? And so we change our coefficient. And this is the main thing that happens. We saw that those group means didn't change those treatment means in our well-designed experiment. But you might see a change in the coefficients when you do this adjustment on a variable that is related to your first explanatory variable. So I think in the slides here, I just kind of talked about who's moving up, who's moving down, who's moving left, who's moving right, and then you can fit this new association. So I get this adjusted coefficient. How do you want to interpret that coefficient? Like before, I would have interpreted this as like, oh, each minute per week you spend sitting lowers your brain volume by that amount. I think this is millimeters. And so it's a slightly less decrease. So how would I change the interpretation of this slope? What was the goal of adjusting? Yeah. And when I do get students, I do complain when students say effect influences, lowers. I do sometimes say the prediction, right? This at least lowers the prediction. So what am I changing about the interpretation here? Yeah, after adjusting for age, what does that mean? And so maybe this idea of if I compare people of the same age and one has spent more time sitting than another, then I'm going to predict a lower MTL by that amount for the one who spent one more minute, number of hours per weekday, say, in sitting. So I'm trying to say, I know it's not because of age. There's still this relationship even when I compare people of the same age, right? And again, there's some other terminology you'll see out there. I don't think these are important for the students. You can think a little bit about how the adjusted slope takes the original slope and then changes based on the relationship of the response with your potential confounding variable. But this isn't the best example because this is not that impressive of a change. Why is this not changing so much? I said the whole problem is we now have this observational study, so things are going to change. Why didn't they change much here? And you can explain in terms of the visual, maybe in terms of the equation. There's still a lot of variability because when I brought into account age, yeah, age may not be that related, but actually more important, age and sitting weren't that related. So they didn't look that different because age and sitting were not strongly associated. So even though this wasn't an experiment, it's possible I don't have to adjust for these other variables, that they're already balanced, right? That I have similar age distributions across the sitting levels, things like that. So maybe I don't need to adjust for that other variable. What do you think? And this, I have learned with my students, I need to really highlight when these are prediction questions, right? I just want to know what you're thinking. There's no right or wrong answer here, and different people give different arguments that are all valid. I just want you engaging in that statistical thinking a little bit. Do I still need to adjust for age? If I looked at this data and decided that age and sitting weren't related, then I can ignore age. Doesn't hurt. Did it hurt to put it in the model? right? It didn't change things. And then the benefit is I can say I did adjust for age, especially when there is this long history of research saying age is important in this particular case, right? It's nicer. I don't think it helps me draw a cause and effect conclusion, but I can at least say that's what's been considered a very important potential confounding variable, and we adjusted for it. And that's all I get to do with observational studies. So I do want to make sure I've adjusted for these important variables, and it may not make a difference, right? And what they end up doing in this study is you can throw all these in. You can throw in all your other variables, education, ethnicity, right? And then you can go maybe to your ANOVA table. And again, students don't need to understand all the details of this. They just need to realize, okay, very weak evidence that sitting matters when you've adjusted for all these other variables, right? And they can still go back to the idea that it matters more than just the amount of exercise, right? But if I compare people that have the same characteristics and what I think are important variables, right, there's a little bit of evidence that the amount of sitting matters. And then that's just a much stronger conclusion to say I've adjusted for these other important variables. Still not cause and effect, because this is still not an experiment, but at least I've done that adjustment. Oh, and so you can try some other ones. I was trying to find something that made a difference. Education, and this is why I put impact in quotes. Again, I'm not trying to draw cause and effect conclusions. Education, you saw a little bit more of a change in those coefficients because you had a little bit more of a relationship between education and sitting, whatever that means. Then maybe have a conversation about, is it okay to treat education level as a quantitative variable? And I always want my students thinking about, is it okay to fit a line through these means, or do I need to bring it in as a categorical variable? And we talk about pros and cons of that. We also tried the sex variable, which was not associated with either variable. So it's not a confounding variable, but, and let me show you this one. Let me take out everything but sex here. Right, so again, I'm going to do my adjustment. Doesn't make much of a difference, right? But that's a very different question, right? So now I would interpret this coefficients. If I compare a male to a male, this is the impact of sitting. If I compare a female to female, this is the impact, in air quotes, of sitting. Very different from the idea of an interaction that Soma was talking to you about. We can do an interaction here. So that means move that categorical variable into the subset by box. That allows those slopes to vary. And actually, I see something very interesting here. Even though sitting was not related to sex, there's an interaction between sex and sitting. That takes my students a long time to understand the difference between those two phrases. And I think that's very important. And so I think it is nice to show them a lot of examples, even just graphs, right, of how those equations could be different, even if sitting's not a confounding variable, because I had a similar distribution of the average amount of sitting between males and females. But very different from talking about whether the slope, the rate of change for sitting difference between males and females. All right. And so I think it's important to investigate those interactions as well. This is showing those means are the same, but that doesn't have anything to do with whether or not there's an interaction. So now that we have this is the final model. I guess I did a different variable here. It's a little bit more significant. Again, this is back from the article. And I liked how it talked about, explores the associations of these variables simultaneously, right? And I think we need to move students beyond thinking about one variable at a time, but just how these things might be interplaying simultaneously. Another thing we're working on in the applet, if you go back to that high or low level of activity, putting that as a response variable and essentially fitting a linear logistic regression. And can we make that simple and visual and something they can understand with a lot of extra work? And that would really expand their toolbox or their ability to think about different relationships. So let's go back to the first example. So I'm going to now ask you to look at a smaller subset of that King County data, just 2000, just for simplicity. I also scaled the price and the square footage, but I didn't do any transformations. And we can put that into the multiple variables applet, and you'll see Then maybe this is a little bit easier to interpret. So if I increase square footage by 1,000, which is maybe a little bit better change, how does that impact the price, $310,000? And so they can think about that relationship. So Alan's given you that version. I'm going to try this version. See if I can do the URL. All right, so here's our price, and here's our square footage. And here's our equation. So now I want to adjust for number of bedrooms. What did you conjecture would be the relationship between price and number of bedrooms, positive or negative? Positive. All right, so I'm going to put bedrooms in here. I'm actually going to put it at the second one. So this is the relationship between price and bedrooms. There's your nice positive association. But what if you only looked at the black dots? What if you only looked at the red dots? What if you only looked at the yellow dots? What if you only looked at the blue or white dots? Right? So if I want to adjust for size, I'm going to change the prices. These are now the size adjusted prices. I'm going to change the bedrooms based on size because there might be a relationship between them. This is now my adjusted association. This is my partial correlation between price and bedrooms if I'm comparing homes of the same size. I get a negative association. Again, it's not super strong. I'm only explaining 50, 60% of the variation. Can you give me an interpretation or an explanation for this negative coefficient? Why does the coefficient become negative when I do this? Bedrooms would be smaller. Why would they be smaller? So we're thinking about interpreting this coefficient as I increase the number of bedrooms. Finish my sentence. But I have the same size house. So I'm increasing the number of bedrooms, but I'm keeping the size of the house the same because we adjusted for size. And so, yeah, I'm going to have a lot of small bedrooms, might not be a very attractive house. And we're seeing a stronger relationship here between my two explanatory variables. And it turns out that that adjustment, like that equation I showed earlier, could be extreme enough that you can change the size of the coefficient. This is actually back to day one, Simpson's paradox, right? When I adjust for this other variable, I might get a different relationship than the unadjusted relationship. And so again, not the most interesting data set, and this doesn't always work with these data sets, but you can often see that idea of, okay, fix the house size and increase a different variable. And so it changes a lot. I think we need to be a little bit more careful on how we have students interpret these coefficients and this idea of, just back to the idea, I can't generally increase the number of bedrooms totally independently from the size of the home. So it's really hard to interpret that coefficient of bedrooms without considering the size of the home and thinking that those aren't related to each other. All right. I think I'm pretty close there. So again, back to this idea of comparing two houses of the same size, right? And again, these are predictions or on average, not trying to sound too causal. I could add an interaction. If I wanted to explore an interaction, the only way to do that is to put it in the model and then see what it tells you, which is a little bit different from this adjusting for the other variable. This is just what's called a surface plot. I do need to go beyond the applets now to do some of these fancier features, but maybe you can start to see I could fit a line here that's going to be much flatter, but I'm going to fit a line up here at bigger square footages that is more negative. And so we're seeing how that coefficient of bedrooms is actually even more negative when I have an increase to the square footage. And so at least in the second course, I do want to be able to get to my students to this idea of a interaction between two quantitative variables. And then also thinking about what's the best way to represent that to people. And I would just say, oh, if square footage is 1,000, what's your coefficient of bedrooms? If square footage is 6,000, what's your coefficient of bedrooms? And really just thinking about how that slope is changing depending on the value of square footage. And so just kind of break it down into those smaller pieces, I think is good for the communication skills. And then in the handout, so back if you were following on what's posted on the website, it doesn't let me go up here when I have Zoom on. Two other examples to draw your attention to, and we can talk more about them if you want. But this is another quantitative by quantitative interaction, which I think makes some sense in context, and I think is interesting for students to think about. And can they do that just based on the numbers, right? So this was about salaries and how salaries go up with experience, salaries go up with education, but then what's this negative interaction? So this idea of kind of diminishing returns. I'm not saying that the relationship turns negative. I'm just saying the impact, again in air quotes, of increasing education may get smaller for people with high levels of experience than people with low levels of experience. And also seeing if they can interpret it both ways, right? So the impact of experience is going to get smaller for people with higher level of education than lower levels of education. So again, just wanting them to be able to interpret these results that they're being shown. And then another study we didn't talk about at this workshop is giving students a memory quiz. There's sequences of letters. They have to memorize the letters in order, and you present the letters in different frameworks, like how they're grouped together and are they recognizable chunks or not meaningful chunks. But we also have set it up on a form that you can make your own URL as an instructor, and then you can just give your instructor specific URL to your students, and then you can download the data just from your students. And so the other questions it asks them is how much caffeine they've had and how much they've had to sleep the night before. And so again, they could bring these variables into the model. I'm really just trying to compare the type of sequence, but let's make sure these other variables aren't getting in the way. Let's make sure that random assignment really did work. And so you can think about adjusting for other variables, even in the experimental setting as well. So if that's something you're thinking or trying to use, or we have example data for that as well, we can talk about that later as well. All right, but I will go ahead and stop here if I can get out. The question came up yesterday about assessment. We did talk a little bit more about assessment at the ECOTS workshop. And so again, at that EA Post website, if you go to workshops and go to the ECOTS one, session 8 had some materials and a separate handout on some homework and exam questions I've used. And then the presentation had some in the slides as well. And I gave you the one today about just picking whether putting or driving is more important. But we're thinking about ways to kind of organize that. So if you just want to go to, assessment questions, there'll be a spot for that as well. Or if you want to contribute some as well, I think that would be wonderful. I will stop sharing.
Thanks very much. We do have a few minutes for our Q&A, either for Beth or for any of the presenters yesterday or today. Before I stop talking at the moment, I'm going to post the workshop evaluation form link into the chat. If you would take a few minutes to fill out the form and say what you enjoyed, suggestions for future workshops. We also ask suggestions for things this group can do to support you as you're teaching statistics throughout the year, whether it's online office hours or more virtual workshops or any ideas you have along those lines. So you've already given us a lot of your time, for which we're grateful. But if you give us another 5 or 10 minutes, not necessarily right now, but sometime in the next week or two, filling out the evaluation form, we'd appreciate that. Questions for Beth or other presenters today or yesterday? Like Beth said at the beginning of her presentation, I want to thank you all for coming and hanging in there. I think I'll stop the recording now.